Quantum computers are real. IBM has one, Google has one. There are companies right now spending billions of dollars building them. And yet they cannot do too much useful. Let's say, not yet. Not because the hardware is too slow, not because we lack the algorithms. The reason quantum computers are not useful today is simpler and stranger than most people realize. They make too many errors. And fixing those errors, that turns out to be one of the hardest problems in computer science. That problem is called quantum error correction. And in the next couple of minutes, I want to give you a real understanding of what it is, why it is so hard, and why solving it matters. Let me start with a quick picture of what a quantum computer actually is. If you want a deep dive, I highly recommend Free Blue, One Brown's recent video on Grover's algorithm. He explains quantum computing beautifully. For our purposes, here is what you need to know. A classical computer stores information as bits. A bit is either 0 or 1. A quantum computer stores information as qubits. A qubit is a two-level quantum system. Think of it as a tiny arrow that can point anywhere on the surface of a sphere. When you measure a qubit, you get 0 or 1, just like a classical bit. But before you measure it, the qubit exists in a superposition, a combination of both 0 and 1 simultaneously. Here's where it gets interesting. If you have 100 classical bits, you can store one of 2 to the 100 possible states. If you have 100 qubits, the system exists in a superposition of all 2 to the 100 states at once. That exponential scaling is what makes quantum computers potentially so powerful for certain problems. But, and this is critical, qubits are fragile. Any tiny interaction with the environment, a stray electromagnetic field, a vibration, even a single photon, can disturb the qubit and introduce an error. This is the fundamental challenge. Now let me show you why fixing quantum errors is so much harder than fixing classical errors. In a classical computer, if a bit flips from 0 to 1 by accident, you fix it with a simple trick. You store 3 copies of every bit. If one of them flips, the other 2 outvoted. Majority wins, error corrected. Can we do the same thing with qubits? No. And the reason is one of the most fundamental laws of quantum mechanics. It is called the no-cloning theorem. You cannot make a copy of an unknown quantum state. It is not a limitation of our technology. It is a mathematical impossibility provable from the basic equations of quantum mechanics. So we cannot store 3 copies of a qubit the way we store 3 copies of a classical bit. But there is a second problem that is even stranger. When you measure a qubit, you destroy it. The act of looking at a qubit to check for errors collapses the superposition. The quantum information is gone. So you cannot check for errors by looking at the qubits, at least not directly. And there is a third problem. Classical errors are discrete. A bit either flipped or it did not. Quantum errors are continuous. A qubit can rotate by any tiny angle in any direction. There are infinitely many ways a qubit can be wrong. So, to summarize the situation, you cannot copy qubits. You cannot look at them to check for errors, and the errors themselves are continuous. This sounds impossible, and yet it is not. In the 1990s, Peter Shor showed something remarkable. You can protect a qubit against errors, not by copying it, but by spreading its information across many qubits in a clever entangled way. The idea is called a quantum error correcting code. Here's the key insight. You take one logical qubit, the qubit that carries your actual information, and you encode it into a larger number of physical qubits. The information is not stored in any single physical qubit. It is stored in the relationships between them, in the entanglement pattern across the whole system. This means a single qubit can be corrupted, and the logical information is still intact. Now, how do you detect the error without measuring the qubits and destroying the information? This is the clever part. You measure not the qubits themselves, but relationships between qubits, parity checks. The mathematical structure underlying most modern quantum error correcting codes is called a Tanner graph. It is a bipartite graph, 2 types of nodes. On one side, variable nodes representing the physical qubits. On the other side, check nodes representing the parity checks. An edge between a qubit node and a check node means this qubit participates in this parity check. When an error occurs on a qubit, it flips the syndrome bits of all the check nodes connected to it, the pattern of which checks triggered. The syndrome is your clue about where the error happened. For simple codes, you can figure out the error by hand. But modern codes have hundreds or thousands of qubits, each connected to multiple checks. The syndrome is a vector of hundreds of bits. The space of possible errors is astronomically large. You need an algorithm to decode it, and you need that algorithm to be fast, because in a real quantum computer, errors happen every few microseconds. You need to correct them before they accumulate. This is where the bottleneck is. Let me give you a concrete sense of the scale of the problem. IBM's current leading quantum error correcting code, called the bivariate bicycle code, has 144 physical qubits encoding 12 logical qubits. To characterize how well this code performs, researchers need to run millions of simulations. Each simulation inject random errors, run the decoder, check if the logical information was recovered. Do this 10 million times across many different error rates. On a standard CPU, using the best open source decoder available today, this takes hours, sometimes an entire day. That means every time a researcher wants to test a slightly different code, they wait a day for an answer. That is not a minor inconvenience. That is a fundamental bottleneck on how fast the field can move. The solution is to run the decoder on a GPU. The core computation inside every decoder, a mathematical operation called Gaussian elimination over binary fields, is embarrassingly parallel. You can process thousands of syndromes simultaneously on a single GPU. The speedup is not to underestimate. The same computation that takes hours on CPU takes minutes on GPU. That difference, hours to minutes, is the difference between running one experiment per day and running 100. That is what my library is building, which will be made open source once the first stable version is reached. GPU native decoders for quantum error correction. Open source, pip installable, vendor agnostic, because the infrastructure for the quantum era should be accessible to everyone. Let me close with where this is all heading. In December 2024, Google's quantum team published a result that the field had been waiting for decades. They demonstrated that their error correcting code actually gets better as they add more qubits. That is the threshold, the point where quantum error correction starts working in practice, not just in theory. IBM has published a roadmap to fault-tolerant quantum computing within this decade. Microsoft, Quantinuum, and a dozen startups are racing toward the same goal. The consensus in the field is that fault-tolerant quantum computers are coming. The question is not if, the question is when. And the answer depends largely on how fast we can solve the engineering problems. Error correction is one of the last unsolved pieces. The decoder is one of the last bottlenecks. If you're curious about how the algorithms work, belief propagation, OSD, LSD, let me know and I will cover this in the next video. If this was useful, share it with someone who has been asking you what quantum error correction actually is. I was in that exact spot not long ago and did not quite know how to explain it. Now you can send them this instead. Thank you for watching.